Hi kiddos, this is module 21.4, mutually exclusive and overlapping events, or geometry. Our essential question is how are probabilities affected when events are mutually exclusive or overlapping? So again, we have to understand what mutually exclusive means, right? So that's a key idea, or overlapping, and we'll get to those. So our answer is basically the probability of mutually exclusive events is the sum. Okay, so again, that means addition of the individual probabilities. While the probability for overlapping events is the sum of individual probabilities minus the probability that both events occur. So it's like mutually exclusive. Only one event can actually happen in one trial. Okay, but overlapping means, well, there's also the probability that both events can occur. Okay, so if you think both, that's overlapping. If you think, well, it's one or the other, that's the mutually exclusive one. All right, so probability of mutual exclusive events. So two events are mutually exclusive events if they cannot, okay, keyword, cannot both occur in the same trial. So a good example that they give us here is basically if you were to flip a coin, it can't land on heads and tails in the same trial. So you can't flip a coin and land on both at the same time. Those two different events are mutually exclusive. So it's not like, let's say, heads and tails. It's going to be heads or tails. Okay, it can't be both. It's either one. That's mutually exclusive. All right, so example one. We got a dodecahedron. That's a 12-sided dice. Okay. And they're saying, what is the probability that if you roll this, that's funny, it's not really a cube, is it, if it's a dodecahedron? And the result is even or a 7. Okay, so notice how they have two different events here. An even number, and we'll say that's going to be group A or set A, or a 7, which we'll call that set B. All right, so, oh, yep, they did that. So set A is an event where you roll an even number. So let's think about all our even numbers. And again, this is from 1 through 12 because it's a dodecahedron. So let's see. 1 is not in there, right? 2 is. 3 is not in there. 4 is. 5 is not in there, but 6 is. Oh, 7. 7's in B, right? 8, that's an even. 9 is not involved. 10 is. 10's an even number. 11 is not. And then 12. So if you notice right away, using this Venn diagram, I was able to basically break down what was in my my sets. All right, so again, group B is the event that you roll a 7. Let S be the sample space. So sample space is including numbers 1 through 12. It just happens to be that, again, group A is only the even numbers, and group B, or set B, is the 7. Now we completed the Venn diagram. Now let's calculate all our probabilities. Now the probability of A occurring, well, that's the number of elements that we have in A divided by our sample space, and we have 6, right? We have 6. 1, 2, 3, 4, 5, 6 possible even numbers out of our sample set, which again is 12. So that's our sample space. And 6 out of 12 is, well, we could reduce that 1 over 2. So there's a 50% chance you're going to roll an even number. Now we have to calculate the probability of event B. Well, that's the number of elements that are in set B. Oops, sorry, I don't know why I put a 7 there. It should be a B. So the number that are in set B divided by our total sample space. So we have one element, 7 itself, out of the 12. Okay, so we have a 1 out of 12 of rolling a 7. All right, so let's go ahead and calculate. This is part D. Calculate P, the probability of A or B. Well, for our total sample set, we have, again, 12 sides for our dice. Now, the numbers of A, so this is for the numbers of elements in A or B. Now, the numbers for A we have is 6. The numbers for B is 1, so we're talking about the elements, the number of elements. And add them together, and there are 7 possible elements that can happen in either A or B. So again, we have 7 that can happen out of our sample set, which is 12. Now we're talking about the probability, not the number of elements. Okay, so whenever you see the P there, again, you should be thinking, okay, probability. All right, so the probability of rolling a even or a 7 is 7 out of 12. Pretty good odds. All right. Now let's go ahead and calculate the probability of A plus the probability of B, and we compare it to step D. So the probability for A again was 1 out of 2. I'm going to go ahead and leave it as 6 out of 12. Okay, and that's from over here. Plus the probability of B, which again was 1 out of 12. If we add those together, 6 plus 1 is 7, common denominator, and look at that. So if you notice, the probability of A plus the probability of B, that should equal the probability of A or B. So that's a little something something you should probably be aware of. That's pretty important. All right, so let's move on. So the probability of overlapping events. Now this process is used from previous Explorer, and we'll get to that. So basically, we already had this concept that I kind of starred earlier, right? Where if A and B are mutually exclusive events, then the probability of A or B should equal the probability A plus the probability B. Now, two events are overlapping or inclusive events if they have one or more outcomes in common. All right, so we're going to actually be using this idea of the addition rule. So if you want to find the probability of A or B, it's going to equal the probability of A plus the probability of B minus the situation where the probability of both events occurring. Okay, so it's not like they're exclusive, they overlap. All right, so you have to factor in the fact that both events could happen, unlike the exclusive one where it couldn't. All right, so let's go ahead and look at the example. That way we get an idea. It looks like we're still working with a dodecahedron, and that means we have 12 sides. And let's see, the result is an even number, or the event, or a number is greater than 7. Ooh, they're changing this up. All right, so we got event A, I think, and event B is where we roll a number that's greater than 7. Yes, and that's what they say here. Okay, and event B is where we roll a number greater than 7. And let S be the sample space, right, which is, again, 12 sides. All right, so our sample space is 12. Okay, let's do this. So if we roll a 1, that's not in group A or B, it's out there. If we roll a 2, okay, that'll be an even number, and it's less than 7, so it doesn't belong to B. If we roll a 3, 3 is just out there. He doesn't belong to A or B, right? He's not even, or he's not greater than 7. We roll a 4. That's an even number. Okay. We roll a 5. Oops, sorry. 5. That doesn't belong to either A or B. We roll a 6. Hey, look at that. Belongs to even. We roll a 7. And again, greater than, not greater than or equal. So 7 is not greater than itself. It has to be greater than 7. Okay, so that doesn't include in B. Let me think. 8 is even, and it is greater. So look how 8 is actually being shared, right? It's A and B. It's the intersection. All right, What about if I roll a 9? Well, 9 is greater than 7, but is not an even number, so he goes in, set B. If I roll a 10, 10 is even, and it's also greater than 7. I roll 11, that's greater than 7, but not even. I roll a 12, that is even, and also greater than 7. Okay, so there's our new Venn diagram for our situation. Now let's go ahead and start breaking this down. So let's start with the probability that we actually roll an even number. Well, how many even numbers do we have? And this is where you're thinking, okay, well, do I count all 6 or do I just count the ones in group A? Well, probability of A, 8 is an A, 10 is an A, 12 is an A. So those all those elements are in A. So we actually have 6 elements, okay, that belong to A. All right, so again, the probability of A is just the number of elements that are in set A divided by the number in our sample space. So we have 6 in A, and we have 12 sides. And again, probability is very similar to, or exact, from our last example. All right, moving on to probability of B. All right, so it's got to be, and this is where we have to be careful because B is now an event where you roll greater than 7, and I want to underline event B elements twice. And look at that, I got 5 of them. All right, so there are 5. Again, the number of elements in B divided by our sample set will give us the probability for B. So we have 5 out of 12. All right, so there's a 5 out of 12 chance that we will roll a number greater than 7. All right, here we go. Now we're going to calculate the probability of A and B. So if we think about it, we have to look at the intersection. All right. Intersection. That means the piece in between. So the probability of the intersection of A and B, well, we have 3 elements there. So let me go ahead and rewrite this to where I could say the number of elements in the intersection of A and B are 3. Okay, so we have 3 over there. Out of our sample set, which again is 12. All right, so what we're really doing here is sample set, still 12 sides. Okay, and that's how we get that. All right, we can reduce. That's 1 out of 4. All right, so there's a 1 out of 4 chance that you're going to roll an 8, 10, or 12, which will satisfy both A and B. So a number that's even or greater than 7. Not bad odds, not bad odds. All right, now we're going to finish off E. So we're going to look for the probability of A or B. So this is the union. So let's take a look here. A or B. So we actually have, and I'll tell you what, I'll go ahead and underline each element 3 times. So 2 is in A, 4 is in A, 6 is in A, 8 is also in A, 10 is also in A, 12 is also in A, and 9 is in B, 11 is B. So I'm considering all the elements in both A or B. And we actually have 8 elements. Okay, we actually have 8 elements there. So again, the number of elements that are in A union B are 8. And again, we're going to still take that out of the sample set. Still 12 sides. All right, we can actually reduce, and that it'll be 2/3. Okay, both 8 and 12 have a GCF of 4. So 8 divided by 4, 2, and 12 divided by 4, 3. So 2 out of 3. Okay, much better odds. Okay, so if you were betting or something like that, you can bet that you would have the probability of A or B occurring more often than 1/4. That's something nice to know. All right, so let's review real quick. The probability of A was 1 out of 2, right? 50% basically. And the probability of B was 5 out of 12. Okay, we already got that. And A and B was 1 out of 4. And I'm going to go ahead and rewrite these to where you kind of see the math here. But 1/2 was really just 6 out of 12. And what I'm doing here, I'm rewriting the probability of A, which was up here, 6 out of 12, plus the probability of B, which was 5 out of 12, okay, from over here, minus the probability of A and B, okay, which was 1 out of 4, which I'm going to write it as 3 out of 12. All right, so 6 plus 5 is 11. 11 minus the 3 right here should give me 8. And that's 8 out of 12. I can actually reduce, and that's 2 out of 3. So there's a 2 out of 3 chance of me basically getting this to get me, what was it? Oh yeah, it was basically to get me a number that was not just even, but also greater than 7. And if you actually look, these are the same. Okay, so that kind of comes with my rule that P or the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. So those are equal to each other. Pretty cool. All right, so let's move on to our tables here. Probability with two-way tables for data. We use tables all the time to make sense of things, especially if you want to make an educated decision. Now, what we're doing here is we're trying to find the probability of a senior or a girl. So basically, the person you select has to be a senior or a girl. Right, so first things first, let's figure out probability of seniors. That's one thing we care about. And the other event is if we pick a girl, okay? And then the probability of a senior and girl, because again, to get us the probability of senior or girl, we have to take the probability of senior plus the probability of our girl minus the probability of a senior and a girl. So see how I'm using the formula from earlier, the other relationship that we noticed from earlier, okay? So this is something really important to be aware about. Okay, so let's do this. All right, so probability of a senior. Okay, I'm going to go ahead and call, yeah, I'll go ahead and call it. I'll just write it out. Probability of a senior. Okay, so first things first, we got some numbers here. How many seniors, well, how many kids do we have? We have 808 kids, so that's our sample set, right? And then seniors, ooh, okay, so there's a number of our seniors. Okay, so we have 202 seniors out of the 808. I can reduce, but for right now I'm not going to reduce. I'm just going to leave it like that. But that's basically the probability or theoretical probability of me selecting a senior. Now let's go ahead and find the probability of picking a girl or drawing a girl, or I don't know what their selection methodology is, but all right, so let's see. First things first, how many girls we have out of the seniors? Okay, so we have 108. So notice how I'm focused on a whole different event. All right, but wait. Oh no, not just senior, no, not senior girls, girls entirely. Notice how that's a big difference, right? I'm thinking seniors still, but in reality, I'm just thinking about girls, all right? Like that Beastie Boy song, girls, da, 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 da. Okay, so it's not just, I'm not focused on the senior aspect of it now. I'm looking at the total number of girls. So we actually have 412 total girls out of, again, our sample set, which is 808. All right, good. And I can reduce, but for right now, I'm not going to. Okay, I'm just going to leave it like that so we can do some computation later. All right, probability of senior and girl. Okay, so let's make sure we do this one right. We have 108 girls that happen to be seniors. So notice how that already gives us on a table. Those are both seniors and girls, so that was very nice. All right, so they gave us 108 out of our sample set, which is 808 still. Okay, so let's go ahead and do this. Now to find our probability of senior or girl, okay, we have to get our probability of seniors. So let's see, I'll write it here. Or girls equals, so the probability of seniors was 202 kiddos out of 808, plus our probability for girls, which was 412 out of 808. So notice how it's like you're adding the two possible events that can happen, and then you're subtracting basically the intersection, which was 108, where they're both in there, right? They're both seniors and girls, okay? All right, so we could do this in your calculator real quick. We have 202. Now there's a reason I didn't reduce. It's because I had a common denominator 808, so the math is a little bit easier towards the end. So 202 plus 412 plus 108. Oops, not plus 108. Silly me. 202 plus 404 minus the 108. And I have 498 out of the 808. I can reduce, but I'll tell you what, I'll just give you a percentage. That's 61. Well, it's actually 0.6163, but if we were to leave that in decimals or percentage, that'd be 61.63%. So that's a pretty good likelihood that you're going to pick a senior or a girl. Okay, that's going to be a common stat. All right, your turn number 1. I want you to find me the probability of headache or no medicine. So again, you have to think about what's the probability of a headache, what's the probability of no medicine, minus the probability of headache and no medicine. So it's the same idea. So again, I'll go ahead and put it here. This is going to equal the probability of headache, plus the probability of the medicine, of no medicine, sorry, no meds, minus the probability of a headache and no meds. All right, so get going and be aware of what your sample set or sample space is, and yeah, let me know. There's your homework. If you guys have any questions, feel free to ask. Take your time with it, okay? It's meant to, you know, pay close attention to detail. They're stories. They're not just numbers. All right, guys, have a good one. And, oh, that dog's adorable.